Hi, I'm Miss Igo. Welcome to my classroom. Today we're going to talk about solving linear equations. First, let's go over some definitions that you need to know. An equation is a mathematical statement of equality. It's a collection of numbers, variables, operation symbols, and most importantly, an equal symbol. If it doesn't have an equal symbol, then it's simply an expression. But the equal symbol makes it an equation. A linear equation, which is what we're specifically going to be solving today, is an equation that can be written in the form ax plus b equals c, where a, b, and c are real numbers, and a does not equal 0. If a were 0, then when we multiplied the a, or 0, times x, it would get rid of that variable, and therefore we would no longer have a linear equation. A linear equation also has a variable to the first power only. So if instead of having ax plus b equals c, if we had ax squared plus b equals c, that would no longer be a linear equation. A solution set is the solution to the equation that makes both sides of the equation equal. This is also the way that we can check to make sure that our answer is correct. Whatever we get for our variable at the end, if we take it and plug it back into the original equation, if both sides of the equation equal, then we know that that is a solution. This is an example of a linear equation. When we're solving a linear equation, there are a few steps that we need to follow. The first step is to get rid of any parentheses or grouping symbols that we see in the equation. Well, this equation doesn't have any parentheses or grouping symbols. The next step is to collect like terms that are on the same side of the equation. Well, first of all, let's review what like terms are. Like terms are any terms that have the same variable raised to the same power, or constants. If you have two constants, those would be like terms. If you had terms with variables that are different, like 3x and 5y, those would not be like terms because the variables are different. If you had 3x and 5x, those would be like terms. But if you had 3x and 5x squared, those would no longer be like terms because they're not raised to the same power. So if we look at this equation, we don't have any like terms that are on the same side of the equation. So now we want to work on isolating the variable. Here is our variable. And I like to think of it as unwrapping a present. If you have a present in a box with wrapping paper on it, you can't open the box without taking the wrapping paper off first. So we always undo addition and subtraction first, or you can think about it as we always work with what's farthest away, just like the wrapping paper. If this is my present, this is farther away than the 3. The 3 is touching the x. The 1 is not. So we're going to work with what's farthest away first. So to get it away from that variable, we have to do the opposite operation. Right now we have a plus 1, and the opposite operation would be to subtract 1. So I'm going to subtract 1. And anytime we're dealing with an equation, we want to keep our equation balanced by doing the same operation on both sides of the equation. So I'm going to subtract 1 from the other side of the equation. All right, so my 1's cancel out, and I have 3x equals 13 minus 1, which is 12. Okay, so now the only thing left that's on the same side of the equation as the x is the 3. When a variable and a number are touching each other, then that operation, or the operation represented, is multiplication. So the opposite operation of multiplication is division. So we're going to divide both sides by 3. 3 divided by 3 is 1, which would give me a 1x, or just x. So that's why we usually say that these cancel out. They're not actually canceling out. They're actually turning into a 1. So we have a 1x, but anytime we have a 1 in front of a variable, We don't usually write that 1. And then we have 12 divided by 3, which is 4. So, like I said earlier, we can always check our solution to see if it's correct. And the way that we do that is we plug it back into the original equation. So I'm going to plug 4 in to my x in the original equation. So that gives me 3 times 4, which is 12. And 12 plus 1 is 13. So because my equation balances, or it's the same on both sides, then I know that this is a solution to my equation. Here's my next example. Again, if we go through the steps of solving a linear equation, we want to get rid of grouping symbols first, which we don't have. We want to combine like terms that are on the same side of the equation, which again we don't have. So now we want to isolate the variable, and we're going to work with what's farthest away first, or undo addition and subtraction first. So this -2 is not touching the x, it's farther away, so we're going to start with it. And to get rid of it, I'm going to add or do the opposite operation. This is -2, so I'm going to add 2. Okay, so that gives me a -5x equals 15. And then to get the x by itself, the -5, that's not a -5, that's a -5 that's being multiplied times x. So to undo it, I'm going to divide by -5. So that gives me x is equal to -3. And again, if I want to check my answer, all I have to do is plug it into the original equation and multiply it out. So a -5 times a -3 would give me a +15. And 15 minus 2 is 13. So I know that this is the correct solution, or this is the solution set to my equation. In this next equation, if I go through the steps, again, I don't have grouping symbols and I don't have like terms on the same side of the equation, but I have a variable on both sides of the equation and I have a constant on both sides of the equation. Now I can choose whatever term I want to move first. It doesn't matter. I could move the 16x, the -8, the 36x, or the 7, and I would get the same answer. Sometimes it's said that you have to move the variables to the left side and the constant to the right side, and that's just not true. You can go with whichever one you want. I'm going to subtract the 36x. That's a +36x. So to undo it, I'm going to subtract 36x. And then I have to do the same thing to the other side of the equation. I'm not going to do it to the 8 because it's not a like term. I'm going to do it to the like term. So I'm going to subtract 36x from 16x. So this gives me a -20x minus 8 equals 7. So if I want to isolate this variable, remember we're going to undo addition and subtraction first, or work with what's farthest away first. So I'm going to add 8. That gives me a -20x equals 15. And then to get rid of that 20, it's touching the x. That means it's being multiplied. So to undo that, I'm going to divide by -20. So that gives me x equals, this is a -15/20. And anytime we have a fraction, we want to reduce our fraction. So the biggest number that can divide evenly into 15 and 20 is 5. So if I ask myself, okay, how many times will 5 go into 15? It would be 3 times. How many times will 5 go into 20? 4 times. So my answer is a -3/4. This next equation has everything on one side of the equation. I always say when you're solving a linear equation or any equation, try not to get your equation lopsided, which means don't try to put everything on one side equal to 0. What I see happen a lot of times when students do that is they'll take the equal sign and just stick it back into the equation, and then that messes things up. So if you are choosing, try not to get your equation lopsided, but here they gave us a lopsided equation, so there's nothing we can do about that. So let's go through our steps. There are no grouping symbols, but there are like terms. So if we look on the left side of the equation, we have several like terms. This 5x and this negative x, those are like terms. And then the negative 9 and the positive 5 are like terms. So let's combine our like terms. Now remember, when we're combining like terms on the same side of the equation, we don't do the opposite operation. If I want to combine these x's, this is just 5x minus x. We're not moving anything over to the other side. So 5x minus 1x would be 4x. And then negative 9 plus 5 would be negative 4 equals 0. So now we want to isolate the variable, and we'll do that by adding 4 to both sides of the equation. And now we have 4x equals 4, and then divide by 4, and that gives us x equals 1. Okay, now we finally have an example that has some parentheses, and that's the first thing we want to do is get rid of those parentheses. And we get rid of the parentheses by distributing or using the distributive property. And that property says whenever we have a number or a term that's touching the parentheses, we distribute that term to everything inside the parentheses. And the operation that we use to distribute is multiplication. So I'm going to distribute the negative 4 into the parentheses, and that gives me a negative 4x. Let me redo that. And then negative 4 times negative 3, that would be a positive 12. Now, we look to see if there are any like terms. There are not, so we're going to isolate the variable. The first thing that I would do is subtract 12. And that gives me a negative 4x equals negative 14. And then I divide by negative 4. And I have x is equal to, that would be a positive 14 over 4. That can be reduced because 2 can divide evenly into both of those numbers. And when I divide each of those by 2, I get 7 over 2. And so that is my solution. When you have an equation like this that has brackets and parentheses, the brackets mean the same thing as the parentheses, and the reason why brackets will be used sometimes when there are multiple sets of parentheses is just to break it up and help you to see what bracket or parenthesis goes with the other set, the other side of the set. So when we're dealing with multiple sets of brackets or parentheses, you want to deal with the innermost set first, which would be this set right here. So to get rid of that set of parentheses, I'm going to have to use the distributive property. And what I'm distributing is this negative that's touching the parentheses, not the 2x. It's not touching the parentheses. So if I distribute that negative, you can think of it as a negative 1. And I'm going to multiply it times each term in the parentheses. Okay, so this is going to stay the same. And then negative 1 times 5x would be a negative 5x. Negative times positive would be a negative 2. equals the rest of this. Okay, so now you can distribute that negative into the brackets or combine like terms. It doesn't matter which one you do first. I'm going to go ahead and combine these two like terms first. So that would give me a negative 3x minus 2 equals 2. And then let me go ahead and get rid of these parentheses. So to get rid of those parentheses, again, I would distribute what's in front of it. Well, the only thing in front of it is a plus sign, which would be the same thing as a positive 1. Well, if I multiply anything by positive 1, it doesn't change the terms. So basically, it's the same as just dropping these parentheses. So that would be plus 2x plus 7. Okay, now to get rid of these brackets, I'm going to distribute this negative, or negative 1. So a negative times a negative would be a positive 3x. Negative times negative would be plus 2 equals, now I'm going to combine these two terms. 2 plus 7 is 9 plus 2x. Okay, so we're at that point again where it doesn't matter what we move. We can move any one of these four terms. I'm going to subtract the 2x from both sides. So 3x minus 2x is 1x, which is the same as x, plus 2 equals 9. And then subtract 2 from both sides, so I get x equals 7. And that is my solution. If I wanted to check this answer, I would need to plug the 7 in, or substitute the 7 into the equation everywhere there was an x. So it would have to go in all three of these places in the original equation. All right, this one looks a little overwhelming, but don't be overwhelmed. Again, we want to start with the innermost set of parentheses first, which would be this right here. So to get rid of that parenthesis, I'm going to have to distribute this negative that's touching the parenthesis. Okay, so that would give me a negative 3 minus 4x. Then I have a minus 2x equals, on this side of the equation, I have a set of parentheses. I can go ahead and get rid of that by distributing this 2. So that's minus 9. That would be plus 2, and then minus 30x. Now let's combine like terms. 2 minus 3, that would be minus 1, or negative 1, minus 4x equals minus 2x. Then on the other side of the equation, negative 9 plus 2 would be a negative 7 minus 30x. Now to get rid of this last set of grouping symbols, these brackets, I'm going to distribute this 7. So that gives me a negative 7 minus 28x minus 2x equals negative 7 minus 30x. Okay, so I have a negative 7, and then I'm going to combine these two like terms, negative 28 and negative 2x. That'd be a negative 30x. Okay, now I want to get my x's together, so I'm going to add 30x to both sides of the equation. And when I do that, my x's cancel out, and I'm left with negative 7 equals negative 7. Anytime I'm working out an equation and my variables cancel out and I have just numbers, if my numbers make a true statement, then that means that I have infinitely many solutions. Infinitely many solutions. Or we could say that our solution set is all real numbers. So let me explain that to you a little bit. We're dealing with linear equations. And so a linear equation, or a solution to a linear equation, is, if we think about it graphically, when we think about the Cartesian coordinate system with our x and our y axis, excuse my not quite straight lines. So if we have an x and a y axis, a linear equation, if we were to graph it linear, it would be a line. And the solution to our linear equation would be where our line crosses the x-axis. That's why most of the time when we solve a linear equation, we get something like x equals 5. It's where it's crossing the x-axis. Well, if we instead had a line that, instead of being diagonal and crossing the x-axis, if it were a horizontal line, again, excuse my drawing, a horizontal line, and it touched our x-axis at every point, then that would mean that our solution is all real numbers. Because it's touching the x-axis, or the solution, the root of the equation, is all real numbers every place that it's touching the x-axis. We have one other possibility if we had a Cartesian coordinate system. That is not good. Where our line was parallel to the x-axis. If a line is parallel to something, then that means it never crosses that line, so there would be no solution. So if it looks like this, this is a conditional equation, and it has one solution. This would be considered an identity, and it has infinitely many solutions. And then this last one would be considered an inconsistent equation, and it has no solution.